So here's the second round of questions from John in Boston. I want to answer these questions because, well, I've already answered them in the book, but I mean, might as well just go over it again. It's a good reminder, a good refresher for myself, and I like to go ahead and review this stuff. That way, people can see the reasoning behind it. The reasoning actually grows stronger as the days progress, and the dogma is starting to do an about face with their acceptance of the nebular hypothesis and their eventual disintegration of that whole thing, because the nebular hypothesis doesn't make any sense at all. And we'll see. We'll give another reason why there's a much better theory than this theory, and as I make these videos. Hi, Celeste. Now, there are three main systems in a thermodynamic, the classical thermodynamics. There is an isolated system, a closed system, and an open system. With an isolated system, there is no exchange of heat or energy, and there is no exchange of matter. Think about something being in a black box. No matter can come out, no matter can come in, no light can come out, no light can come in. It's isolated. A closed system has an exchange of energy, so light can enter and light can exit, but matter can't enter and matter can't exit. The best way to, well, I know it's kind of not true, but the idealization of a closed system is think about it like a window. You can shine a beam of light through a window and it will go through the window. But, you put your hand on it, your hand isn't going to go through. As a window would be surrounding a closed system. An open system would be exchanges of light and exchanges of matter. An open system would be like a boiling pot of water. So you have the heat coming off the water that's coming out as thermal radiation, and you also have the water boiling and going into steam and escaping the pot. That's an open system. Now, there might be some, dare I say, delusional physicists that believe that isolated and closed systems exist in nature. They don't. In nature, everything is open. Everything has an exchange of matter, and everything has an exchange of light. Some more so than others, but the whole thing is that these are idealizations. There's only open systems. Those are only systems that exist in nature. The reason why they have isolated and closed systems is to do engineering projects and for abstraction purposes, to make it to where the math is easier. You can remove variables if you make the systems that you're referring to as isolated or closed. It helps more. They're more isolated or they're more closed than as if they were like in a boiling pot of water. You put the lid on the water, you can make it somewhat of a closed system where you don't allow the actual water vapor to escape, like a pressure cooker, only without a vent on it. As well, isolated system, you would put a lot of insulation around that pot of water too, and make sure it's completely locked off from the world. But in essence, that's an idealization. It's not reality. Unfortunately, John asked me here, he says, after a star is born much later in its life, when it is living on its life on its own transformation curve, it can be best characterized as a closed system, an open system, or an isolated system. Well, all stars are open systems. Let's get that out there. All stars are open systems. They exchange light and matter with their environment. To say that they're a closed system, I think that happened in the 1920s and 1930s. And they had stars modeled as closed systems because, well, the gravitation is really strong. And it made it easier to try to say, well, this math equation works for here, and then we can just do all these models for how a star is supposed to work. Unfortunately, what happened is back in the 1920s and 1930s, they modeled stars as closed systems because it was easier for them. And then they could do their equations and say, well, the star is in local thermodynamic equilibrium with its environment. And then they could just ignore all the variables, which would include the light and mass coming out of the star. See, they don't want mass coming out of the star when they did their equations. They had to have all the mass stay there. That way everything worked out down the line. They had to remove that mass loss variable. And like I said, unfortunately, we know stars are open systems because we observe stars that have lost the majority of their mass. Earth, for one. Earth, originally I'd called it a black dwarf. I would say more along the lines of Mercury being a black dwarf. Earth is like a late stage ocean world. Earth has one 330,000th times the amount of mass that the sun has. And that's a huge amount of mass loss. And that's only possible if stars are open systems. They lose their mass as they evolve. And all stars lose their mass as they evolve. All stars lose their heat and light, and all stars lose their mass as they age. Now, they become less open as they evolve because less percentage of their mass is lost to atmospheric escape and radiation and what have you. And the properties of the star change, which make it leaning more towards a closed system. But that happens slowly over many hundreds of millions of years as the star evolves. And I think that's more appropriate to model a star as an open system because that is what we observe. And the big thing here is a mathematical model of something. If the observations directly contradict the mathematical model, then the mathematical model becomes completely useless. And in fact, it becomes something of a what word would describe that? It gets in the way of scientific progress. If you are a mathematician and you have a model and you model stars with these perfect formulas and these perfect ideas, these idealizations and abstractions, with a model that ignores a huge variable, and that variable in this case being mass loss, then what happens is you don't understand what happens to the star as it cools and dies. And that's why a lot of astronomers, they have stars as always shining and always being really massive. And if they were to go back and look at the stars, they would see that there's solar wind coming out of it, there's coronal mass ejections, there are flare events, and that signals that there's mass loss. There isn't a glass window completely covering the sun and all stars. That mass is coming out. And that mass loss will continue for the entire life of the star. Outer space is a huge place for that mass to go to. I guarantee you that. It's a very large place. They say, where's all that mass? Where's all that mass? Well, the mass goes back into outer space to make new stars out of. It just recycles itself perpetually, infinity. And that being said, it's very dangerous to have mathematicians working on things that are physical in nature, because they sort of lose track of reality with their equations. Bill Gates had taught me that very early on. Of course, I started learning about the purposes of mathematical equations and how they abstract away a lot of meaning. And I was also taught in my physics classes in college and in high school that you always put the you always put that little what's that one word called? The qualifier next to the number. For instance, if you have 100, you have 100 what? 100 kilograms, 100 centimeters, 100 molar mass of something. If you don't have a qualifier next to a number, then the math is completely worthless. And a lot of the times when I study these astrophysical explanations for things, what they do is they sort of remove all the meaning and they abstract into oblivion these really complex ideas. But they're not complex. I mean, yeah, maybe they are complex, but there's a difference between thinking deeply and thinking clearly. And you can be a very deep thinker and be quite insane. And I think that's what happened with a lot of these astronomers. They've gone into an insanity land, and now they think that stars, when they cool and die, that they can keep all their mass. Of course, they model them as closed systems. They keep all their mass, and this mass somehow contracts and eventually becomes what they call a black hole of some epic science fiction novel type black hole type thing. And that's very strange seeing those ideas, especially since there aren't any black holes in nature. I don't know why they even teach that. But that's what happens when you don't understand what it is you're looking at and you try to model things based off of idealizations and abstractions, and you ignore a lot of variables that make or break the theory. I just wanted to throw that out there. I've been thinking about that for a while. And here's another question. He says, over the lifetime of a stellar object, is there a physical mechanism by which a stellar body can gain mass rather than lose mass? Well, yeah, a star can gain mass, but as it evolves, it loses more mass than it gains. The net mass loss is greater than the net mass gain. And a good example would be like, say, the sun would absorb a bunch of asteroids, rocky objects. But in turn, the sun will coronal mass eject a whole bunch more stuff to keep its equilibrium, and then keep on losing that mass as it continues evolving, which is a really strange phenomenon. I remember seeing a few videos of a comet or a large body entering the sun, and then I don't know how much of the time lapse it is or how fast the reaction was, but that body would enter the sun, and then it would throw the equilibrium of the sun off. Some equilibrium is there, and then it will eject a bunch of mass to make up for that extra mass that it just gained. But that's a whole nother subject. I didn't even write about that in the book. I think 300 pages in that book is long enough. But so yeah, there's a physical mechanism by which the stellar body can gain mass. Yeah, it can gain mass, but the net mass loss is greater. Okay, it says here, in terms of mass, do stellar objects live inside closed systems, or instead do they live inside open systems? A stellar body is in the open system. All star systems are open systems. And there's another question here. Okay, final question. Is there a mechanism whereby the universe can inject matter or energy into a stellar body system? If it happens at the birth of the star, can it happen again at a later stage in the life of the star? Well, inject matter and energy. The way I look at that is, okay, say you have the solar system. If you have a rogue object entering in the star system, say there's a random Jupiter, a rogue Jupiter, it's, hauling ass around the galaxy, and it passes by Neptune, or passes by Jupiter, or passes by the sun. There's going to be some effects, and yes, that there would be a gain in energy. I think in terms of like additional angular momentum, and that stuff gets really complex when you start doing orbital mechanics. If you have a large body passing by another one, it'll throw that other body off, and it'll throw everything else off, and there's like this huge cascading effect. But I haven't really worked on that too much. But it's really complex stuff, far over my head at the moment. Yeah, and he also says dynamic and continuous for the transformation curves is better than static and discrete. I think that's a good idea. So basically, in a nutshell, we know stars are open systems because an open system is something that loses mass, gains mass, and loses energy and gains energy. And we have direct observations of very old stars that have lost the majority of their mass. Only the reason why astronomers don't realize this is because they call the very old stars planets. But as we know in this theory, the planet is the highly evolved star. But the bone-headed astronomers, a lot of them won't ever realize that. And a lot of them won't admit that this is a major discovery as well. But hopefully one day the future astronomers that come up and they learn what this thing really is, what the Earth really is, what Mars really is, what the Sun really is, and they make the necessary changes to their theories and see where they went wrong. And it's definitely a privilege of mine to be a very, very small part of that change. All right, John, I hope that helps you. I hope that helps all my listeners. If you have any more questions, feel free to email me. All right, guys, take it easy.